During the first few days of your calculus course, you're going to come across a lesson about limits. In fact, you're probably going to do limits for the first couple weeks. And limits are really, the foundation of calculus. So in this video, I'm going to go through a bunch of examples. I'm not going to do much algebra in this video. I'm going to really just kind of focus on what a limit is and look at some graphs and determine limits graphically. So what you're looking at here is a function on your screen. All right, and this function, of course, is a quadratic. And if we're looking to find the limit of something, right, we want to know exactly what limit means. So the limit of a function basically means the sort of the y value that function is getting really, really close to as the x values get really, really close to something. So if we were to say the limit lim of our function as our x values get really, really close to, let's say, 2, what that's actually asking is for us to take a look at x equals 2, which is right down here. So when x gets really, really close to 2, go up and find the y values and see what the y values get really, really close to as they approach from the left and from the right. And it looks like that y value is 4. So the limit is the y value, or the output value, that the function approaches as the x values get closer and closer to 2. Now those x values can get closer and closer to 2 from the left. In other words, it can go from like 0, 1, 1.5, 1.9, 1.99, 1.999, and so on, infinitely close to 2. And from the right, they can go 5, 4, 3, 2, maybe 2.1, maybe 2.001, 2.0001, infinitely close to 2. So you're sort of squeezing in from the left and from the right, and you're determining what value, what y value your function is giving you. All right, so that's really the idea of a limit, right? The function that's on your screen is actually x squared plus x minus 2. All right, so if I put that right here, right, and we plug in 2, and this is like what we call direct substitution. If we plug in 2, we get 2 squared plus 2 minus 2. So it's 4 plus 2 minus 2. 4 plus 2 is 6, minus 2 is 4. So a lot of limits are going to equal the y value when you directly substitute in this value right here that x is approaching. Sometimes that's not going to work, but a lot of times it's going to. But in this video, we're mainly going to focus on the algebra of, or not the algebra, but the kind of the graphing connection, the visual limits of this idea. All right, so let's go ahead and quickly calculate the limit of this function as x approaches 0. So x approaches 0. 0 is right here. Go down and find your graph. You want to figure out the y value that the function is approaching as the x values get closer and closer to 0. So let me zoom in on this a little bit and we can see a little bit better. So as my x values get closer and closer to 0, so I'm squeezing in on 0, what is my y value getting close to? Well, it looks like it's getting close to -1, -2. All right, so my limit of my function, the limit of the function as x approaches 0, is equal to -2. Now, at this point, it's probably worth mentioning the one-sided limits, the notation for that. The limit of our function as x approaches 0 from the left, we'll put a little minus up there. From the left is -2. So that's just this one as it approaches from the left. And the limit of our function as x approaches 0 from the right, so that would be coming in from this direction, is also -2. And when those match up, we have an overall limit at the function in general. All right, so I'm going to really kind of dive into that a little bit more in subsequent limit videos, but this is really just an intro. So let's look at this one right here. We have another parabola. All right, it's flipped upside down because of our negative lead coefficient, and it's a little bit more complicated than just -3x squared. I threw this sort of these binomials in the numerator and denominator, and what that does is gives us a domain restriction. It restricts our domain so x cannot be 1. Because if you plug in 1 right here, you get 0 on the bottom of the fraction. That's not allowed. So our domain is restricted at when x is 1. Now what that means is when x is 1, there's a hole in the graph. So I'll draw a little hole in the graph. When x is 1, this is 1. And this looks like it's about -3. Alright, so that is kind of an interesting thing. If I were to answer this question, what is the function value when x is 1, I would get undefined. There is no value because it's not in the domain, hence the hole right there. But if I look at the limit of the function as x approaches 1, let's take the function in from the left-hand side and from the right-hand side. And I want to think about what the function is approaching, what y value the function is approaching as the x values get closer and closer to 1. So if we squeeze in from the left-hand side and from the right-hand side, the y values are getting closer and closer to -3, even though there's actually a hole in the graph right here at 1, -3. It doesn't matter. You don't have to have a value there to have a limit there. And that's a really important concept. You don't have to have a value to have a limit. The idea of a limit is that it gets infinitely close to that point, but it never actually has to touch it. All right, we can make these assumptions in calculus based on this idea of like the infinitesimal difference, or this really small change as we get closer and closer to a value, right? The limit can exist if the function value does not. Moving on. Next up, again, we have a domain restriction. X cannot be -2. So at when x is -2, there's a hole in the graph. So I'll put a hole in the graph right here. So if I look for the limit of the function as x approaches -2, even though f of -2 does not exist, it doesn't matter, because the limit doesn't have to actually exist at the value, or I said that backwards. The limit still can exist if the value doesn't actually exist. So I guess my point is, like, we're dealing with +4, so the function is squeezing in on the y value +4 as the x's get closer and closer to -2. So this answer would be +4. Let me zoom back out. +4. Let's keep going. All right, here we have, as you can see, a huge discontinuity here, which we'll talk more about in additional videos about discontinuity. But you can see that the domain is restricted, obviously. The denominator cannot be 0, so the x value that makes that denominator 0 is not in the domain. And that is, of course, a vertical asymptote right here. The function doesn't exist there. So as we look at the limit of the function as x approaches 3, here we have to do two one-sided limits. So from the left and from the right. Oops. So let's do the left-hand limit first. This is 3, right? When the function approaches, when the x approaches 3 from the left, we're coming in this direction. The y value seems to be approaching positive 5. And when I come in to 3 from the right-hand side, the y value is getting close to negative 5. Now, since these don't match up, the overall limit does not exist. Right? In other words, generally, when the function, when the x value gets closer and closer to 3, the function is way up here, and then it's way down here. They don't come together, so the limit does not exist. All right, piecewise function. All right, you can see that we have a linear function here, x minus 2, and then we have this little dot here, 1 comma 4, which leaves a hole in the graph. All right, so if I were to ask you what's the limit of our function as x approaches 1, here's positive 1. You would come in from the right, and you would come in from the left, and you would say that the graph gets close to negative 1. Even though the function value has a jump discontinuity up here, that's okay. If I were to answer this question, obviously it's 4. But the limit as x approaches 1 is negative 1. Again, the limit can exist even if the value isn't there. All right, here we see another asymptote function. We've got ourselves a domain restriction at negative 3, so x cannot be negative 3. So at negative 3, we've got ourselves an asymptote, a vertical asymptote. So the function is going to infinitely get close to that, but it's never actually going to touch it. So it's going to go up in this direction and down in this direction forever. So if I'm looking for the limit of this function as x approaches negative 3, well, you have to look at it as one-sided. So come in from the left, negative 3 from the left. So from the left is this way. Follow the curve up, and you see that it approaches positive infinity. Take the one-sided limit as the x values get close to negative 3 from the right-hand side. So now we're coming in this way. Just follow the curve down, and you see that the values approach negative infinity. They don't come together. The two one-sided limits are not the same, so the overall limit does not exist. All right, same deal here. We have a domain restriction. X cannot be 4, which is why you see this asymptote right here at positive 4. So if we ask the overall general question of what's the limit of f of x as x approaches 4, we have to look at it from both sides. X approaches 4 from the left, so we're coming in this way. Follow the curve up, and you see that it's positive infinity. Look at the function, or the limit of the function as x approaches 4 from the right. So we're coming in this way, and we follow it up. We see it gets bigger and bigger, approaches positive infinity. They're both the same, so the overall limit is positive infinity. So even though there's an asymptote there, the function never actually touches 4. It doesn't matter. As x approaches 4, the y values approach infinity. In other words, this is going to go up like this forever and ever, and as the x's approach 4, the y's approach infinity. This one's a sine curve that has an oscillation in the middle, and this one is really, really crazy. You know, if we were to kind of zoom in on this, you would see that the graph just kind of bounces back and forth between positive 1 and negative 1 really, really wildly as it approaches the origin. And something like this, if I were to ask you the limit as x approaches 0, this would not exist, because it doesn't, if you were to zoom in on this, and I'm not going to, you would see that the graph just keeps bouncing back and forth really, really wildly. the limit does not exist. It doesn't approach anything because it just keeps bouncing back and forth. This one's kind of similar. Right, this one has sort of a damping effect. You know, if we were to graph this, let me zoom in on that a little bit. If we were to sort of follow this sort of line up, you would see that as we get closer and closer to 0 from the left and from the right, the limit of our function as x approaches 0. If you look from the left, it approaches 0. From the right, it approaches 0. So this graph has a limit of 0. All right, because the damping effect is getting sort of smaller. It's kind of like decaying, if you will, towards 0. That's kind of an interesting one. Alright, so that's the basics. What I'm going to do now is show you a bunch of examples here on a much bigger graph. This one does not have an actual function to it. This is just sort of an exercise in the visual limits. So give this a pause. Try all 32 of these problems. See if you can get the left-hand limit, the right-hand limit, the overall limit, and the function value at each of these x values. So pause this now and give it a shot. And here are the answers. I'm not going to go through this right now because the video is about 16 minutes already, but what I will do is put up a separate video that just addresses this particular worksheet. So I hope you enjoyed this video. This is sort of the intro to limits. There's a lot more to it, a lot of algebra, and a lot of different sort of variations on how to find different limits and different scenarios and stuff. But this was really just kind of like the graphical connection. So look forward to my subsequent videos. Thanks for watching.